In 1977, the Voyager 1 probe began its long journey, carrying the human dream of exploring the outer reaches of the solar system. The outer regions of the solar system are cold, vast, and mysterious, far from the heat of the sun and full of unknowns. After Voyager 1 completed its flyby detection of gas giants and their moons, it began its journey out of the solar system and into interstellar space in the 1980s. So, what is the outermost part of the solar system? The mysterious Oort cloud, a hidden treasure of the universe at the edge of the solar system. And this is Cosmos 204, allowing us to watch the bright stars and explore the mysteries of the universe. In the past 40 years, humans have been able to study 8 planets in the solar system and several asteroid belts between the planets. However, the solar system is huge, billions of kilometers in diameter, and the space between galaxies is even wider. Voyager 1 travels at about 17 kilometers per second, traveling nearly 1.50 million kilometers per day. Even so, it will not approach another star until about 40,000 years later, when it has long since stopped working and lost contact with Earth. In this long and lonely interstellar voyage, the probe will cross the icy edge of the solar system and penetrate deep into the boundaries of interstellar space. Eventually, it will become the first man-made probe in history to reach the outermost part of the solar system. So what is the outermost part of the solar system? Not a planet, nor like the asteroid belt of the inner solar system. In fact, it is a huge diffuse cloud of trillions of frozen celestial bodies, like the outer shell of the solar system, which may extend to more than a light year's space. This is the Oort cloud. The Oort cloud. The Oort cloud is a hypothetical bubble of frozen celestial bodies that surrounds the entire solar system, ranging in size from tiny particles to mountain-sized fragments. The vast majority of these fragments are composed of water, methane, and many other elements and compounds. The orbits of the planets and asteroid belts in the inner solar system are aligned with the plane of the sun's rotating orbit, and the Oort cloud is a huge, omnidirectional shell of material that envelopes the solar system, believed to be thousands of astronomical units away from Earth's orbit, extending trillions of kilometers into interstellar space. It is the most distant region of the solar system and defines the boundaries of the sun's attractive force, the farthest point from which the sun can attract moons. Here in the Oort cloud, the sun is just one of the brighter stars in the Milky Way galaxy. Because the objects inside the Oort cloud are weakly influenced by the attractive forces of the sun, they do not travel in the same plane or in the same direction. Instead, fragments move and collide with each other. Their loose attractive forces make the Oort cloud particularly vulnerable to disturbances from nearby stars and even the attractive forces of the galaxy itself. These attractive force disturbances can put objects in the Oort cloud in orbit to Earth and the sun, turning them into comets because of the Oort cloud's distance, dim light, and sparse matter. No celestial object has yet been clearly identified in it, but it remains the most widely accepted explanation for the source of distant comets we have observed entering the solar system. The objects in the Oort cloud and beyond the orbit of Neptune are called trans-Neptunian objects, and their distance from the sun increases by orders of magnitude as they move outward. When we pass the orbit of Neptune and the distance from the sun becomes extremely large, we have to measure it in astronomical units rather than kilometers. 1 astronomical unit is the distance Earth travels around the sun, about 150 million kilometers. At 5 astronomical units, 5 times farther away than Earth, is the snow line, which is cold enough for water and other matter to exist in the form of ice, causing more matter to be distributed away from the sun. Neptune's orbit is about 30 astronomical units. Beyond Neptune's orbit is the Kuiper belt, a thick, spinning donut-shaped disk of billions of pieces of ice and rock, a remnant of the solar system's formation. The Kuiper belt, which extends from Neptune to about 50 astronomical units away, contains about 100 million comets. as well as asteroids and planet-like planets, like Pluto, Haumea, Maureen, and even Neptune's moon Triton. Triton is believed to have formed in the Kuiper Belt, one of the most remote places in the solar system, before being captured by Neptune's attractive forces. Even so, the distance is nothing compared to the size of the Oort cloud. The size of the Oort cloud. Light travels at nearly 300,000 kilometers per second from the sun's surface, taking about 4.5 hours to reach Neptune's orbit, and another 3 hours to cross the other end of the Kuiper Belt. Travels for about 10 hours to reach the heliopause. There, the solar wind and plasma radiating from the sun collide with the interstellar medium interstellar radiation, gas, like a galactic estuary, marking the end of the sun's magnetic influence and the boundary of interstellar space. But even in this space, light travels in just 17 hours. At about 123 astronomical units from the sun, the inner edge of the Oort cloud is much farther away, at least 10 light days from the sun, and possibly even farther, well beyond the size of planets and the Kuiper Belt. The inner edge of the Oort cloud is thought to begin at about 2,000 astronomical units, 40 times farther than the outer edge of the Kuiper Belt. And this is just the innermost point. The entire structure is believed to extend to 100,000 astronomical units, more than a light year into interstellar space. So light takes nearly 2 weeks to reach the Oort cloud, and 18 months to travel through the other end, even at the fastest speed in the universe. The speed of light. The formation of the Oort cloud, over from the early solar system, settled into the planetary belts of the inner solar system, such as the Kuiper Belt. So how did all the matter in the Oort cloud get to such a distant place? Much like the Kuiper Belt, the Oort cloud is thought to have formed at least in part from the remnants of protoplanetary disks that formed the orbital planes of the solar system and the sun. The material condensed into dust and rock, eventually forming large pieces of protoplanetary debris called planetesimals. The early solar system had a large number of planetesimals, most of which were either accreted by gas giants or ejected by Jupiter's attractive forces, especially beyond the snow line, into orbits in remote locations. Trillions of pieces of debris settled into the planetary belt we see in the inner solar system today, but the rest were ejected beyond the planetary range. Most of this material will leave the solar system entirely and enter other star systems, possibly into similar clouds around other young stars. But not all celestial bodies will be lost to space. Some planetesimals stabilize when they reach interstellar space. They are not far enough from the sun to be completely free from the attractive forces of the sun, but far enough away for the region's main attractive force to influence tidal forces from the Milky Way. Now, with a combination of weak solar attractive forces and attractive forces from the rest of the Milky Way, objects in the Oort cloud circle the sun like worms around night lights, hovering in the Milky Way's no man's land. The Oort cloud may also have captured star subobjects from other star formations within the same solar nebula. Recent simulations of the early solar system show that the sun formed in an embedded open cluster of 200 to 400 stars, which were initially closer to each other and later drifted individually to the vast interstellar distances we see today. Most of these stars have protoplanetary disks and remnant debris that is either swallowed by their planets or ejected. As these stars move away from each other, the debris is scattered, exchanged, and then dropped into a spherical shell that resembles what surrounds us. Therefore, a large number of Oort cloud objects may be the product of the interaction and exchange of attractive forces between the sun and its neighbors, and perhaps most of their matter originated outside the solar system. The source of all comets. We have known about the Oort cloud for 70 years, but its existence has not been conclusively confirmed. The main evidence supporting its existence are long-period comets. Scientists agree that the Oort cloud is the source of most of the distant comets we observe entering the solar system. Comets are rocks and ice from the outer solar system that travel along orbits towards the sun. Since comets are frozen most of the time, as they approach the sun, the surface ice evaporates, forming a comet's coma behind the celestial body, which is the comet's most distinctive feature. If the comet survives vaporization and the encounter with the sun, it passes by the sun and leaves the solar system again, where it refreezes until it returns again. After dozens or hundreds of round trips, depending on the orbit, comets eventually disintegrate, and can never be seen again. There are several different types of comets that enter the solar system. The first are ecliptic comets, also known as short-period comets, which travel within 10 astronomical units of the sun and along the ecliptic plane of the sun. Most of them come from the Kuiper belt or discrete disk, another extrasolar disk scattered by Neptune's attractive forces. The other type is a long-period comet, which takes more than 200 years to orbit the sun, so it enters the solar system very infrequently. Most of the known long-period comets have been seen only once, and the vast majority have gone undetected. Some comets have extremely long orbits, and they last entered the solar system before humans appeared. The earliest thought about the origin of these comets was by the astronomers Ernst Öpik and Jan Oort in the early 1930s. Öpik speculated that the most distant comets originated from an orbiting cloud in the outer solar system. In 1950, Jan Oort revised this idea to explain the abundance of comets we observe in our solar system today. Because most comets are primitive planetesimals that have existed for 4.50 billion years, it is common sense to assume that most of them have either vaporized or crashed. However, even today, we still see a large number of comets in and out of the solar system. Oort predicted that there must be a so-called library of comets in the outer solar system, a source of celestial bodies that can survive the years and always retain comets. Similar to Öpik's prediction, Oort also noticed that the orbits of a large number of comets take them to about 20,000 astronomical units from the sun, suggesting that the source of the library of comets may be around this distance. He also found that long-period comets entering the solar system appeared to come from all directions and did not coincide with the ecliptic plane. From this, he concluded that the library must be a spherical structure, rather than a belt or disk like the Kuiper belt. He predicted the existence of an icy shell of comet nuclei, relatively uniform in distribution, like clouds rather than bands, hence the name Oort cloud. Jan Oort laid the groundwork for revealing the nature of the Oort cloud, and over the past few decades, our understanding of its structure has deepened. We now know that the Oort cloud can be divided into two parts: the large spherical shell discussed earlier, and another smaller, ring-like internal structure, Hill's cloud. This ring structure, also known as the Hill's cloud, is a giant circumstellar disk that marks the beginning of the Oort cloud, 2,000 astronomical units away, and extends to at least 10,000 astronomical units, and may even be 2 or 3 times as far away. Unlike the spherical outer Oort cloud, the Hill's cloud is more similar to the Kuiper belt, albeit thousands of times larger. We know about the existence of the Hill's cloud because it holds the key to solving the mystery of the Oort cloud's apparent self-healing capacity as a repository of long-period comets. It is estimated that the Hill's cloud contains the highest concentration of comets in the solar system, containing at least 5 times more comets than the outer Oort cloud, and possibly more. And these comets are often ejected into the orbit of the outer Oort cloud due to attractive force disturbances. Over time, new objects are replenished to the outer Oort cloud to replace those lost as long-period comets. In addition, the Hill's cloud may also be filled with comets from another source, the scattered disk. About half of the objects in the scattered disk eventually enter an outward orbit, eventually reaching the Hill's cloud, which indirectly provides material for the Oort cloud. Sedna. We have never identified an object in the outer Oort cloud, but the asteroid Sedna, discovered in 2003, could be a Hill's cloud object. classified as a planet-like object. Composed mainly of water, methane, and nitrogen, it is about 3/4 the size of Pluto and orbits the Sun very far away. Sedna takes about 11,500 years to orbit the Sun on its extremely slender and elliptical path, which brings it to 76 astronomical units at its closest approach, and nearly 1,000 astronomical units at its farthest. It is currently about 85 astronomical units from the Sun and is currently heading back into interstellar space. The Minor Planet Center, MPC, the official organization responsible for collecting data on asteroids, classifies Sedna as a scattered object. However, this classification is controversial, and Sedna's wide-angle orbit is much farther than that of a scattered object such as Eris. Eris is about 97 astronomical units farthest from the Sun, and Sedna's orbit would take it farther. So it has been speculated that it is a Hills cloud object. However, it has not been confirmed, and there may be various other natural explanations for the strange orbit of this strange planet. Outer Oort cloud. The Outer Oort cloud is more dispersed than the Hills cloud, and estimates of the number of objects it contains vary, but roughly there are 2 trillion. As many as 1 trillion of these objects may be more than a kilometer in diameter, but each is tens of millions of kilometers away from each other. The total mass of the Outer Oort cloud is unknown, but with Halley's Comet as a reference, the total mass of its outer shell is about 5 times the mass of Earth, possibly slightly less. Such a small amount of material is distributed over an unimaginably wide space. Therefore, it is still difficult to find small and faint celestial bodies in it. Only when attractive forces affect the tidal forces that perturb one of these celestial bodies, such as a passing star or the Milky Way galaxy, sending it into orbit towards the Sun, will it appear in our field of vision as a comet. Over the years, we have recorded such examples: Comet Spring, Comet Hale-Bopp, Comet Lovejoy. The closest of these is Comet Spring, an Oort cloud comet discovered in 2013 and approaching Mars the following year. As it vaporized near the Sun, astronomers detected elements such as iron, nickel, potassium, zinc, chromium, and magnesium. At the time of discovery, it was about 7 astronomical units from the Sun, but its orbital period was so long that it would take at least 740,000 years to re-enter the solar system. Another example is Comet Hale-Bopp, discovered in the summer of 1995. It was the most widely observed comet of the 20th century, visible to the naked eye for about 18 months. It was the brightest comet observed in decades, and the longest on record. Comet Hale-Bopp was found to contain argon and krypton levels 25 times lower than the solar system average. The 2 discoveries suggest that Comet Hale-Bopp was below minus 238 degrees Celsius for most of its life. Therefore, it is thought to have formed in the Kuiper Belt, migrated to the Oort cloud, and re-entered the solar system millions of years later as a long-period comet. Finally, Comet Lovejoy, discovered by amateur astronomer Terry Lovejoy in 2011. The comet is classified as a cruise sungrazer, a special type of comet that orbits very close to the Sun. In 2011, Comet Lovejoy did, approaching the Sun and passing through the corona, appeared intact on December 16th, but was greatly affected by the intense radiant heat of the Sun. Subsequently, it was visible from Earth during the Christmas holidays, earning the nickname Christmas Comet 2011. Future missions to the Oort cloud. Although we have never identified an object in the Oort cloud, at least 5 man-made spacecraft will eventually make their way there. But these are not 5 dedicated missions. They are the interstellar probes of previous missions, namely Voyager 1 and Voyager 2, Pioneer 10 and Pioneer 11, and New Horizons. At the moment, Voyager 1 is the farthest and fastest, but the inner edge of the Oort cloud is so far away that these probes would take more than 500 years to reach the Hills cloud and 12,000 to 25,000 years to pass through the other side. By then, all 5 spacecraft would have long stopped working. In the 1980s, there was a concept mission called the 1,000 Astronomical Units, or TOW spacecraft, designed to perform a long-range mission that could travel 1,000 astronomical units over 50 years. Among its many proposed uses, collecting data from the hills and Oort clouds is one. Unfortunately, despite renewed interest in it in the 1990s, the project never got off the ground. At present, the Oort cloud is too far away to be reached and transmitted back with probes in real time. However, we may be able to search for Oort cloud objects on Earth using improved existing technologies. In 2014, another concept mission, the Whipple mission, was proposed to NASA's Discovery program. The mission proposed the establishment of a dedicated observatory to detect Oort cloud objects at a distance of 10,000 astronomical units through transit technology. The principle is to detect celestial bodies passing in front of other stars and blocking some of the starlight. Unfortunately, among the candidates considered by NASA, the Whipple mission was not selected, but received funding to continue its research. Transit technology is a rapidly advancing field of science, so advanced telescopes that can detect exoplanets around stars in the Milky Way may also be able to detect planetary objects in the Oort cloud, because these objects also pass in front of those stars. The Oort cloud outside the solar system. Speaking of other stars, if the sun formed in an open cluster of stars, and there was exchange of matter between the stars, would other galaxies also have shells similar to the Oort cloud? The answer is yes. It is certain that a considerable number of stars in the Milky Way, including most of our stellar neighbors in the solar nebula, there are extrasolar Oort clouds like our solar system, suspended in interstellar space. However, due to the distance between the stars, these extrasolar Oort clouds are difficult to observe. However, if evidence of comets is found in these star systems, there is likely to be some kind of Oort cloud-like source, so it is likely that many galactic stars have their own distant collections of comets. However, these extrasolar Oort clouds may not be a priority when studying extrasolar stars in depth. The universe is vast, and no matter what technology we develop or how powerful telescopes become, we cannot change the insignificance of human beings, Earth, and everything that happens on this incredibly complex planet takes place in a tiny speck of space that is barely visible from its nearest neighbor star. Stellar systems are so vast and distant that humans may never understand another star system, as well as our own. The Oort cloud is one of the many fascinating things we can't see when we look up at the night sky. Every star in the night sky hides the complex structure of its star system. From planets and moons to the Oort cloud, a vast shell hidden in interstellar space that holds the secrets of the universe, waiting to be explored.